Thank you everyone for coming to my talk today. Today I'm actually I think my talk is a continuation of Jeff's talk at the beginning of the conference because um, Jeff talked about how you need to plan for changing requirements, for changing realities, and my talk is going to be a lot about how do you write systems that are resilient to these types of changes. I'm going to talk to you about how does code rot, how does code decay, why does code decay, what does it mean that code decays, how to build systems where the code does not decay or does not rot. And if I were to sum up what my points are, it's going to be that we need to think in terms of systems and not in terms of projects, and that it is not software that we engineer, but rather the software evolution process or the software development process. A few words about me. So, I am a freelance software gardener. You could call it principal engineer as a service. And my job is to upgrade your developers by pair programming and to help you deal with your growing pains. I worked at Orbs, which is a blockchain company for 2 years, and I worked at Wix, where I was head of backend engineering. And I'm a father of these two beautiful children, a partner of this beautiful woman. I'm also a musician, and I play in an actively touring band. This is me here on the right playing in Copenhagen, and I also bake my own bread. So that's about me. Let's talk about why does code rot and how does code rot. So as Jeff said in the beginning of the conference, we don't want to linearly plan our software development. We need to react to changing environments, to changing requirements, and these might come from various reasons. Uh, it could be that the market has changed. It could be that a competitor has come into the picture. It could be that our product is no longer relevant and we might need to pivot. But the point is that we cannot predict in a in any dependable fashion what we're going to develop in a few months. Now, while we do that, we feel that there is a paradox that we cannot invest in quality for our software systems, because if we invest in quality, we will waste the time that we need to develop the features that we think that we need to develop in order to catch the market, to achieve dominance. So we run really fast. We work with a constant sense of urgency, and we feel that we don't have the luxury of investing in quality, in how to develop our software, in making our software maintainable. And so what happens is that we either risk missing our market, or we risk delivering software that is not maintainable, that is rotten, that has decayed. And in many cases, this leads to our softwares being big balls of mud. A big ball of mud is a piece of software that has lost all design, that is not maintainable anymore, that when you want to make a change to it, you have no idea where to make that change. You will just stick it wherever you can and you hope that it will work. And what happens is that successful startups, in most cases, have big balls of mud in their core. And if they are lucky, they might have a developer or a few developers who are vigilant and will work to slowly dismantle this big ball of mud. But in most cases, in the most common case, you have a situation where a startup is 10 years old, a company is 10 years old, and it's still in its core, there's a big ball of mud that everyone is afraid to change. And slowly but surely, our code base decays and becomes unmaintainable. How? How does that happen? How does our code base rot? So I think that first and foremost, And this is also something that Jeff talked about. We think in terms of projects. And projects are something that has a beginning and an end. Now, do you want your project to end? As Jeff asked, what is the end of Amazon, right? What is the end of Google? Software systems, and especially internet based systems, are breathing, living organisms. They are not projects, they do not have an end. And then you might say, yeah, that's perfectly true. Our software system is a living organism, but what about the pregnancy? But what about the first version? How do you build your first version? How do you build your MVP, your minimal viable product? And what I have observed is that in startups and in Israeli startups, which is what I am mostly familiar with, we have what I call an effort worship culture. We really worship and we really want to work hard. We want to work 12, 14 hours a day, eat pizzas, drink beers, you know, be with our pals. It's fun, it's engaging. But in many, many cases, what we develop is not what we need to develop. Because again, we have no idea what our customers are going to need 6 months from now. We have no idea how people are going to react to our software, how people are going to use our software. In many, many cases, software systems are not minimally viable. You have like 80% feature bloat, and people do not use most of your features. And while we do that, while we worship the effort, while we develop MVPs that are not really minimal, we ignore the only meaningful KPI, which is our dev velocity, our dev speed, the speed in which we can react to changing requirements. Now, we know that, right? Because at least some of us are very experienced engineers. We have been around the block and we know that we are going to be in trouble in a few months. And so we try to anticipate these problems and to prepare ourselves to them. We invest in premature optimizations. We invest in premature architectures. We invest in premature infrastructure. And we call that Yagni. You ain't gonna need it because these things, these infrastructures, these architectures, you do not have any evidence that you actually need them. And when you run into problems, they are not going to be what you need. They might even make it harder for you to change your system. And so what happens is that even experienced software engineers inevitably run into fear of change. Fear of change is where I'm afraid to change my software. I have a big ball of mud, I have a monolith, and it's unmaintainable because I am afraid to make changes to it. And then everything slows down to a halt. Now, again, because we are experienced software engineers, we we know that we know that we're gonna run into fear of change. So in many cases, we write tests, we practice continuous integration, continuous delivery. We use things like feature toggles. We employ some sort of an agile process, maybe Scrum, maybe Kanban, maybe Scrumban. But I think that one of the problems is that many people do not understand why they do these things. Do we achieve the goal that Scrum has set to achieve? Do we achieve the goal that TDD has set to achieve? And in many, many cases, the answer is no. And this gives rise to cargo cults. Cargo cult is a word that describes a situation where you practice some sort of a methodology that you do not fully understand why this methodology exists. For instance, if you have CI and you push your build, how long does it take your build to run? Do you go to take a cigarette break, a coffee break, lunch? Do you go home? Do you come back tomorrow and hope that your build has passed? Do you practice something like Scrum or Kanban? How often do you release? Do you have 2 weeks sprints, but do you release every 2 months? If you do that, then you do not really achieve anything that Scrum sets to achieve. Do you have flaky builds? Do you run like long running end-to-end tests, and then when they finish, do you send a forensics team to investigate why did the tests fail, and are these real failures or are they flaky tests. So what happens is that even if we try to solve our problems using methodologies and tools that are common in the industry, we feel that there's nothing we can do to avoid fear of change. There's nothing we can do to avoid our dev velocity grinding to a halt. But I think that actually there is a lot that we can do, and it begins with a changing mindset. We need to start to understand that our job is to maintain software. Our job is not to build software, right? Think about Google Search. Google Search has been with us since 1998. That's 23 years. Google Search has been in maintenance mode for 23 years. Facebook has been in maintenance mode for 17 years. Maintenance is not something bad. It is our job to maintain software. If you start a new software system, you're going to spend a few months building it, right? The MVP. But you hope to spend years upon years upon years on maintaining it. So, first and foremost, you need to accept that you're going to spend most of your time maintaining your software, and you need to make sure that it's easy and fun to maintain it. And you need to understand that your software will always change. Any change that you make to your software is temporary, but the concept of change is permanent. Your software is always changing, is always developing. And this is why I feel that software systems are not something that you construct, they are something that you garden. And I will explain. If you build a bridge, if you are a bridge engineer, what is your job? Your job is to plan the bridge, right? So you do a lot of research. You do geological research. You do climate research. You do traffic research. You need to understand what are going to be the conditions that your bridge needs to withstand. And then you might do some planning, might do some modeling, and then you're going to bring in a construction crew to build your bridge. And if that bridge collapses and people die, you are criminally liable. So you have no privilege of making mistakes. You need to solve everything in advance. Software is not like that. In software, you can always make changes. Unless you're building something that goes on a spaceship to the moon, you are mostly going to be able to release versions of your software continuously. So even if you made mistakes, you can take these mistakes back. You can fix these mistakes. You have a privilege of making mistakes. And this is very much like a garden, because when you build a garden, you do not plan the entire garden in advance. You come up with a master plan of how your garden is going to be laid out. And then you plant your lawns and your trees and your shrubs, and then you wait and you allow it to grow and you nurture it and you feed it and you trim it and you prune it. And yes, you might sometimes remove some of the trees because they have become sick or because they have become irrelevant. Maybe the people who own the garden, they want, fruit bearing trees and not permanent trees. So you will remove some of the trees and you will replace them with fruit bearing trees, but you will never bring in a bulldozer and remove the entire garden and start from scratch. So how can we do that? How can we build software that does not decay? How can we garden our software? So I think it's all about managing our technical debt and about working in an iterative fashion. Let's talk about technical debt. Technical debt has become somewhat of a swear word in our industry. People are afraid of technical debt, but it is a fact that you cannot grow without accumulating technical debt, right? If you work for 3 months or more and you do not control your technical debt, you run into problems. Your code base will decay. But if you spend these 3 months always handling your technical debt, then you will not deliver any valuable feature. So you need to decide which of our technical debt we're going to maintain to pay back and which we're going to ignore. Now it's very easy to do that because the places in your code base that are the hotspots, that are mostly changing, these are the places where you need to deal with your technical debt. And places that change very seldomly, you don't need to deal with the technical debt. It's not a problem. You want to work using some sort of a continuous delivery lifecycle, but you want to distinguish between delivering your software to production and exposing your features to your users. So you can use things like feature toggles and experiments to help you always deliver software without being afraid of exposing like immature software or software that is not ready to your users. And you want to work iteratively. You want to work in small chunks. You want to facilitate emergent design. What is emergent design? This emergent design is where you do not forcefully plan how your software is going to be architected or how your software is going to be engineered. You come up with a master plan like a garden, and then you set it aside and you continuously check yourself from time to time against that assumption, against that master plan, but you do not do any like low level design, any detailed design. You just start to write your software, and by working in small chunks, in short iterations, and continuously refactoring, you facilitate emergent design. You allow the design to emerge. You want to postpone mechanical decisions, like big decisions that you cannot take back, to later stages. For instance, choosing a database system is something that I like to postpone for at least a few months, because when I start writing my software, I have and my software has and my design has emerged. I have a much better idea of how I want my database to behave. What are the requirements for my database system? It's not easy to facilitate emergent design, and a very good way to facilitate emergent design is by using outside-in development. So when I do outside-in development, I use my code and then I implement my code. First, I use my software and then I implement my software. So if I write an API, then I will write code that uses that API. I will I will design the API from the call site, and only then I will implement that API. Now, outside in really helps me do that because it forces me to first use the software and only then implement my software, and it forbids me from doing detailed design. Now, the problem is that outside in development is also something that is often hard to do, because if you write a UI, then how do you use the UI, right? The UI is used by our users, not by code. So TDD, test-driven development, is a very good way to do outside-in development. And in this case, the test uses my UI. So I will start a new system by writing a failing end-to-end test that uses the UI. It could be something like Puppeteer, or something like Selenium, or something like Detox if I develop a mobile application. And I will write a failing end-to-end test. And that end-to-end test is going to be very, very coarse-grained. So if I'm developing, for instance, a bookstore, then my end-to-end test is going to be a customer is able to buy a book. And that's it. The book has no name, no author, no title, no ISBN, nothing, just an ID. But if that test passes, then my system works. I know that it works. And what I do is I walk towards what's known as a walking skeleton. A walking skeleton is a very thin slice of functionality of my entire software system. And the work is done when that working skeleton is deployed to production, is running in production using a continuous delivery process, and the end-to-end test passes in CI. And then I start writing fast integrative tests, because end-to-end tests are slow and they are flaky. I tend to write and a single end-to-end test per use case. For instance, if we have a bookstore, then we have one end-to-end test for customer buys a book and one end-to-end test for store owner updates the catalog. And that's it. I don't need to write any other end-to-end test. They are slow, they are flaky, they are bound to IO, to infrastructure like Docker. They will take minutes to run. And if I have a lot of end-to-end tests, then I will not be able to develop quickly. However, I do want to have high scope tests. So I write a suite of acceptance tests, which are tests that still talk in the language of user stories, and they still exercise the entire software system, but they do not have any I/O. They are isolated from the outside world via what's known as hexagonal architecture. So wherever my software needs to talk to a database, file system, web service, another microservice, you name it, I hide that functionality behind an adapter, and then I implement that adapter a second time using an in-memory implementation, and I start my entire system injecting the in-memory adapters from the outside via hexagonal architectures. I have no mocks in acceptance tests. Everything is real, but maybe faked, but no mocked. I do not program any behavior.
Shai, we need to leave some minutes for some time for questions, okay?
Yes, yes, yes. And then I will start to go to a smaller grain, and I will have fast integrative tests that are in the scope of a single module or a single microservice. So if I have a system that is comprised of microservices, then the component tests will exercise a single microservice, and the acceptance tests will exercise the entire suite of microservices. Again, isolated from I/O via hexagonal architecture. These tests are very, very fast. They run in milliseconds, and they are very, very deterministic. And if I test a microservice that needs to collaborate with another microservice, then that microservice is going to be mocked. I'm going to mock the behavior. Now, I said that I'm going to use a fake version of my adapter for each adapter. So if I have a MySQL book repository, then I'm also going to have an in-memory book repository. But how do I know that that MySQL book repository and that in-memory book repository are equivalent? I will write integration tests, which I name contract test, that run twice, once against the fake and once against the real adapter. And if the same test passes against both implementations, then I know that both implementations are equivalent. They conform to the same contract. Now, I will have very few of these tests, like one for each adapter. They will run with the end-to-end tests, with the slow tests, because they need like MySQL, Docker, something like that. And they will give me the confidence that I can rely on my in-memory fakes for the fast integrative tests. You will notice that I have not mentioned unit tests at all because I tend to not write unit tests unless I see myself writing a component test that repeats again and again and again with the same behavior but different data. For instance, in validation, and in which case I will extract a validator out from the component and I will test the validator itself using a unit test that drives different data into the same behavior. These tests are fast, they are deterministic, but they have a low value because they are very, very small scoped. And I don't want to have small scope tests. I want most of my tests to be in the second quadrant, to be fast and large scoped. I want to have a lot of component tests that are fast and a lot of acceptance tests that are fast and high scoped. And I want to have as few small scope tests as possible to facilitate writing systems that are very, very easy to maintain. If I write a lot of unit tests, if I write a lot of end-to-end tests that are slow, if I write a lot of unit tests that are fast but are small scope, then it will be very, very difficult for me to maintain my software. End-to-end tests, like the slow end-to-end tests, give me a very, very slow feedback cycle, so it's very hard to rely on them for making changes. And the small scope unit tests, they do not provide any value because if I change implementation, then the unit tests for this implementation are no longer relevant. So to sum up, I think that what we need as an industry, as software engineers, what we need is a paradigm shift. We need to stop thinking in terms of MVPs. We need to stop thinking in terms of alphas. We need to start thinking in terms of working skeletons, of thin slices of functionality that we can deploy to production and start getting feedback from our users. We need to stop thinking about big designs, about architecture, and we need to start facilitating emergent design. And we need to stop thinking about our software as construction projects because they are not. They are gardening projects. They are long running. They are evolving. Our job is not to engineer software. Our job is to engineer the software evolution process, the process by which our software evolves. If we get that right, then our software will be maintainable. But if we do not get that right, then we will never be able to maintain our software. Thank you. And if you have any further questions, I have 5 minutes to answer questions now, and I will step into a Zoom room later where I can answer further questions.
So thank you very much, Shai, for the interesting session. We have one question from the audience. Ron is asking the following question. Do you think that when addressing software project within our organization that is sick in the way you explained, as it wasn't being maintained for years, you have to start from scratch to start following the methodology you present today, or you can transform a project being neglected for a long time into a software entity being maintained in an ongoing fashion for years to come?
So it really depends on how rotten the code base is, but yes, definitely. First of all, there's a book, Working Effectively with Legacy Code by Michael Feathers, that deals exactly with this sort of problem. And this is a very common problem because every successful startup is in your situation, right? You have worked for some time, you have neglected your code base, and now you are stuck. Now, when I worked at Wix, my first project at Wix was rewriting the server that serves sites to users. Like it was like the most important piece of software at the time. And it was completely rotten. It was like 5,000 lines of Java in one file. And what we did is we started writing end-to-end tests that set in stone the way that the QA manager understood that how the system needs to behave. So we had some understanding in some people in the organization about how the system needs to behave, but it was never documented. We started documenting that understanding in a series of end-to-end tests of specs that run against a deployed environment. And then we started a process of gradual rewrite. And gradual rewrite is the key. You want to keep your software in production at all times. If you look at the history of software projects, of rewrite projects, most rewrite projects fail horribly because they take too long, because they do not actually solve any problem. And by the time that the rewrite project is done, it is as rotten or more rotten than the system was intended to replace. So unless your system is like a complete mess and there is no way anyone is ever going to be able to maintain it, it's probably better to cover it with a suite of end-to-end tests and then work towards gradually rewriting it. Eventually, after a year, after 2 years, you could throw away the old code base completely. But by that time, there's not going to be a lot of that code base left.